The overall goal of the ST-Nexus project is to develop an integrated approach for organizing and presenting space-time object patterns and relationships within evidence in a way that facilitates the task of the human analyst. The focus of this project is on development and implementation of a mechanism for linking and coordinating powerful and flexible space-time geospatial database and information visualization capabilities. Our work combines an innovative, multi-representation database strategy with diverse visualization techniques for coordinated spatial, temporal, and object-related views within a unified conceptual scheme. Because our approach for visualization of large volumes of complex space-time information relies on multiple linked views, the use of multiple displays is a natural and desirable extension. Not only can various views be laid out by the user into a logical arrangement for given analysis, the large display space allows fine-grained details in complex information to be seen more easily. The user can also back away from the display to gain a high-level impression of the displayed information. The following video shows some of our preliminary results.
The visualization shown here allows an analyst to identify and explore spatial temporal patterns in vehicle movements, crash incidents, and major storm events in relation to radio message logs collected in the automatic position recording system. Multiple screens significantly enhance exploration and analysis in the visualization by allowing analysts to see a large range of spatial and temporal scales at once. In maps and plots of events over time, analysts can interactively adjust compound spatial and temporal filters, observing the results in broad overview or at fine levels of detail. For instance, an analyst might be interested in comparing patterns of movement of emergency response vehicles, including the convergence, coordination, repeating paths, and lagged responses of such vehicles.
I relayed it out for putting on one screen like this, but you can see that the numbers are adjusting, and of course what we'd like to have is the dynamic adjusting of the time for what's being shown.
What's going on here, dude?
This is actually supposed to be a separate map layer. This is kind of like a local zoomed-in motion of a vehicle traveling down streets to a hospital. There are actually multiple hospitals that can be geolocated. Warehouses, police stations, and so on. And then the idea is that we'll be able to track vehicles, track resources, track individual people and responders, and so on, all in this big data model that's being produced by the simulation. Their actual simulations produce 1.6 million people and 200,000 vehicles. And now we've aggregated to 16 zones, so you can imagine the challenge not only in terms of the query language, that level of speed, but also, if we're at a coarser granularity than 16 zones, having much more screen real estate would be a huge advantage.
Using Improvise, we are working with Bruce Campbell and Suzanne Weghorst at the Pacific Rim Visualization and Analytics Center to develop the visualization shown here. A large map of downtown Seattle, divided into 16 zones, displays the health condition of people and the operational state of vehicles, as generated by the RimSim Emergency Response Scenario Simulation software. Expansive screen real estate allows us to explore and analyze geographic aspects of information sources in fine detail. The visualization shown here focuses on county-level aggregation of demographic information collected in the 2000 United States Census. A large map, zoomed in on several eastern states surrounding Washington, D.C., shows the location of airports relative to major roads and urban centers. The color of counties indicates regional demographic variations, from purple areas of high population density to green areas of high average age. A variety of other data views support analysis of relationships between the large number of demographic statistics obtained in the census.
Separating and spreading multiple coordinated views across multiple screens appears to facilitate interaction with geospatial data and maps, temporal data and time series plots, and abstract data attributes and tables by allowing analysts to see, manipulate, and refer to many more pixels.